The 2024 Nobel Prize in Physics honors two pioneers whose work bridged physics, biology, and computation, laying the groundwork for the AI revolution. John J. Hopfield and Geoffrey E. Hinton. They are recognized for foundational discoveries and inventions that enable machine learning with artificial neural networks. Inspired by biological neurons and sharing fundamental similarities with physical systems like magnets, artificial neural networks learn from data. In the early 1980s, John J. Hopfield introduced his influential Hopfield network. This model, drawing on concepts of energy landscapes from physics, showed how a network of simple units could act as an associative memory, storing and retrieving patterns, and even correcting errors. It was a profound demonstration of emergent computational abilities. Geoffrey E. Hinton, over several decades, also made transformative contributions. He co-developed the Boltzmann machine, a neural network that could learn complex data distributions using hidden units. Critically, with collaborators, he championed backpropagation, an algorithm that finally allowed multi-layered neural networks to learn effectively. Hinton then spearheaded the breakthroughs that led to deep learning, devising methods like layer-wise pre-training that made it possible to train the very deep networks powering today's most advanced AI. The foundational discoveries of Hopfield and Hinton are not just behind the AI in our smartphones and search engines. They've also become indispensable tools for scientific discovery itself, from particle physics to predicting protein structures with systems like AlphaFold. Their work, deeply rooted in physical principles, has given humanity a revolutionary new toolkit, profoundly changing how we understand and interact with the world. Every star, a colossal nuclear furnace, eventually exhausts its fuel, leading to some of the most dramatic events in the cosmos. A star's ultimate fate is primarily decided by its mass. Stars like our Sun, after billions of years fusing hydrogen, will swell into enormous red giants. As their core contracts, it briefly fuses helium into carbon and oxygen, but lacking the mass for further fusion, their outer layers drift away, creating a beautiful planetary nebula. Left behind is a white dwarf, an Earth-sized, incredibly dense ember that slowly cools and fades. But for stars born much more massive, 8 times our Sun's mass or greater, the end is far more spectacular. These giants burn through their fuel rapidly, fusing progressively heavier elements until their core is mostly iron. Iron fusion consumes energy, so the star's furnace goes out. Gravity then takes over catastrophically. The core implodes in a fraction of a second, triggering a shockwave that blasts the star apart in a brilliant supernova explosion. This titanic blast scatters heavy elements, forged within the star, across space, seeding new generations of stars and planets. What remains of the core depends on its mass. If it's about 1.5 to 3 times the Sun's mass, it becomes a neutron star, an object of unimaginable density, packing more mass than our Sun into a sphere just the size of a city, often spinning rapidly as a pulsar. However, if the remnant core is even more massive, gravity wins completely. It collapses indefinitely, forming a black hole, a region of space-time so warped that nothing, not even light, can escape. The death of a star, whether a gentle fade or a violent explosion, is not just an ending. It's a crucial part of the universe's ongoing cycle of creation, dispersing the building blocks of life and leaving behind some of the most exotic objects imaginable.